Hello, welcome back to the video tutorial series for Mr. Billingham's AP BC Calculus class. We are now in the very last section of the text. Once again, this section is not covered on the AP exam this year, but it's worth learning and it's not that difficult. Anyway, the book in the previous section on parametrics first spent a while reminding you how parametrics work and then went into the calculus of it. And I split that into 11.2a, the non-calculus part, and 11.2b, the calculus part. I'm going to do the same with polar coordinates. So if you want, you can just skip straight to the calculus part if you remember polar coordinates. Or if you struggle with them a bit, you might want to listen in on this description of them. So in rectangular coordinates or Cartesian coordinates, we use a reference frame, x and y axes, and we describe a point with two coordinates, x and y. And as you know, x describes how far you go left or right of the origin, and y is how far you go up and down. Well, polar coordinates are a totally new way of thinking about it. In polar coordinates, you describe two things. You describe how far away from the origin an object is and at what angle relative to the positive x-axis. And so polar coordinates require an r and a theta. Interestingly, with polar coordinates, there are an infinite number of ways of representing every point, whereas with rectangular, there is one unique way to represent each point. Let's take a look at an example. Consider the polar point 2 root 2 pi over 4. Let's think about that. At an angle of pi over 4, or 45 degrees, we're in the middle of the first quadrant, we go out a distance of 2 root 2. Now what about this guy? Well, in this one, we go, instead of positive pi over 4, we go negative 3 pi over 4. And then in that direction, we go a distance negative 2 root 2. So that would be the same as the previous polar coordinate point, because when you point in a direction and go a negative distance that way, it's walking backwards. Let's practice with these examples. So in A, the point 4 pi over 2 means at an angle of pi over 2, or 90 degrees, or straight up, go 4 units. So that's the point 0, 4. In B, at an angle of pi, go negative 3 units. So go backwards from 180 degrees, 3 units. So that's 3, 0. C, 16, 5 pi over 6. Well, 5 pi over 6 is 150 degrees. It has a 30 degree or pi over 6 reference angle. And so we can use the conversion x is r cos theta, y is r sine theta, just like we did in trig, and we get x is 16 cos pi over 6, which is 8 root 3, or negative 8 root 3 rather, and y is 16 cos 5 pi over 6, and that's 16 times a half, or 8. So the point is negative 8 root 3, 8. And then finally D, negative root 2, negative pi over 4. So in the direction of negative pi over 4, or negative 45 degrees, go negative root 2, which is go up. That looks like negative 1, 1. Now let's convert the other way. They want two sets of coordinates for each, so let's start with A, or 1, 1, 0. Ha! Interestingly, this point is the same, or one representation is the same, 1, 0, in both polar and rectangular. The first one means go right 1, up none. The second one means go out 1 at an angle of 0. And then another one I could use for that would be -1 pi. For B, -3, 3. The radius is 3 root 2 in a direction of 3 pi over 4. Or, of course, I could do -3 root 2 from an angle of 7 pi over 4. For C, 0, -4. One obvious one is go 4 units in the direction 3 pi over 2. Another obvious one is to go -4 units in the direction pi over 2. And for D, 1 root 3. Well, that's a 60-degree angle, and the hypotenuse is 2, so it could be 2 pi over 3, or it could be -2 in the direction of -2 pi over 3. Now we'll try graphing with polar coordinates. So in Cartesian coordinates, if I say graph x equals 2, and you notice there's no y, that means y can be anything as long as x is 2, and that is a vertical line. So how about this? In the first one, they say r is 2. So obviously the distance from the origin is 2, and the angle can be anything. So pretty clearly, that is a circle of radius 2. But how about the next one? Well, go any angle, and from there go a distance -2. You're still 2 units from the origin. So both of A and B have the graph that's a circle with radius 2. The third one, the angle is pi over 6, also known as 30 degrees. So any radius, positive or negative, and that looks like it's going to be y equals root 3 over 3x, a line through the origin. We don't have time to spend on it now, but there are wonderful, beautiful graphs that can be done in polar coordinates. You should have done some of them in your pre-cal or pre-cal equivalent class. But you can graph them with technology, and we'll take a look at how to do that in just a second. To graph these in your calculator, just switch straight into polar mode, and then instead of y1 equals, you'll have r1 equals, and you just enter r1 equals sine 6 theta. And you probably want to let theta go between 0 and 2 pi. But you get a very interesting graph here. These are called roses, and it turns out, if you don't remember, sine of n theta and cos of n theta show only n leaves in the rows if n is an odd number, but 2n if n is an even number. So the first one will show a rose with 12 leaves. The second one, as theta varies, then 2 cos theta can take on values between positive 2 and negative 2, so 1 minus it will take on values between negative 1 and positive 3. Anyway, here's what the graphs look like. So the first one is called a 12-petaled rose. The second one's called a limaçon, after the French word for snail. And the third is just plain old circle. You can use a couple of formulas to convert back and forth between polar and rectangular equations. We've already seen x equals r cos theta, y equals r sine theta. Here's a little list of the formulas that can be used. As I said, x is always r cos theta, y is always r sine theta. That's going to be very useful to us shortly. X squared plus y squared always adds to r squared, and to get theta from y and x, you can take the inverse tan of y over x. Let's use these formulas and convert the previous r equals 4 sine theta that turned out to be a circle. Let's show that it is. So the trick here, and you learn these tricks and get comfortable with them, is to multiply through by r. r squared was always x squared plus y squared, and r sine theta is 4y, or r sine theta is y, so 4r sine theta is 4y. So this becomes x squared plus y squared minus 4y is 0. We'll add 4 to both sides to complete the square, and we'll get x squared plus y minus 2 squared is 4, which is a circle centered at 0, 2 with a radius of 2. Now I'm going to go to Desmos and graph r equals 4 sine theta. And you can see when I graph in Desmos r equals 4 sine theta, we do in fact get a circle with radius 2 centered at 0, 2, just as the math support. Interestingly, you can graph any polar equation in parametric form using the following trick. A polar function has the form r equals f of theta. Now, x is r cos theta, so if I multiply this through by cos theta, I get x is r cos theta, which is f of theta cos theta. And similarly, y is r sine theta, which is f of theta sine theta. So I can, if I want, I can suddenly rename theta t, and I can graph it as f of t cos t, f of t sine t. Then because it's parametric, I can do things like animate, etc. Here's a picture of that circle with the 12 leaves done in both polar and parametric form. I got Desmos to graph r equals sine 6 theta, 0 to 2 pi, and then I did what we discussed and put it in parametric mode, and here's the second graph. This time, as we mentioned, I did it in parametric mode, sine 6t, cos t, sine 6t, sine t, identical graph. Sometimes that can be useful. Anyway, thank you very much. You have been a great audience, and I appreciate you. Wish I was in the classroom with you. Hope you continue to prepare for the AP exam. We have just a few weeks left. Anyway, stay healthy, and here's a meme for today. And thanks again to the meme guys, Michael Kaufman, Luke Arambidi, Ryan Brown, and Marshall Mann. One video tutorial left, and that's it. Stay tuned for my favorite meme.